The ethynyl radical is an organic compound with the chemical formula CCH. It is a simple molecule that does not occur naturally on Earth but is abundant in the interstellar medium. It was first observed by electron spin resonance isolated in a solid argon matrix at liquid helium temperatures in 1963 by Cochrane and co-workers at the Johns Hopkins Applied Physics Laboratory. It was first observed in the gas phase by Tucker and co-workers in November 1973 toward the Orion Nebula, using the NRAO 11 meters radio telescope. It has since been detected in a large variety of interstellar environments, including dense molecular clouds, Bok globules, star-forming regions, the shells around carbon-rich evolved stars, and even in other galaxies. Astronomical importance. Observations of C2H can yield a large number of insights into the chemical and physical conditions where it is located. First, the relative abundance of ethynyl is an indication of the carbon richness of its environment. Since there is typically insufficient quantities of C2H along a line of sight to make emission or absorption lines optically thick, derived column densities can be relatively accurate. Observations of multiple rotational transitions of C2H can result in estimates of the local density and temperature. Observations of the deuterated molecule, C2D, can test and extend fractionation theories. One of the important indirect uses for observations of the ethynyl radical is the determination of acetylene abundances. Acetylene does not have a dipole moment, and therefore pure rotational transitions are too weak to be observable. Since acetylene provides a dominant formation pathway to ethynyl, observations of the product can yield estimates of the unobservable acetylene. Observations of C2H in star-forming regions frequently exhibit shell structures, which implies that it is quickly converted to more complex molecules in the densest regions of a molecular cloud. C2H can therefore be used to study the initial conditions at the onset of massive star formation in dense cores. Finally, high spectral resolution observations of Zeeman splitting in C2H can give information about the magnetic fields in dense clouds, which can augment similar observations that are more commonly done in the simpler cyanide. Formation and destruction. The formation and destruction mechanisms of the ethynyl radical vary widely with its environment. The mechanisms listed below represent the current understanding, but other formation and destruction pathways may be possible, or even dominant. In certain situations, formation in the laboratory, C2H can be made via photolysis of acetylene or C2HCF3, or in a glow discharge of a mixture of acetylene and helium. In the envelopes of carbon-rich evolved stars, acetylene is created in the thermal equilibrium in the stellar photosphere. Ethynyl is created as a photodissociation product of the acetylene that is ejected into the outer envelope of these stars. In the cold, dense cores of molecular clouds where N greater than 104 cm-3 and T less than 20 K, ethynyl is dominantly formed via an electron recombination with the vinyl radical. The dominant creation reactions are listed below. C2H3++ E minus C2H plus H plus H. C2H3++ E minus C2H plus H2. CH3CCH++ E minus C2H plus CH3. C3H plus OC2H plus CO. Destruction. The destruction of ethynyl is dominantly through neutral reactions with O2, or with atomic nitrogen. Ion-neutral reactions can also play a role in the destruction of ethynyl, through reactions with HCO plus and H3 plus. The dominant destruction reactions are listed below. C2H plus O2HCO plus CO. C2H plus NC2N plus H. C2H plus HCO plus C2H2 plus CO. C2H plus NC2H2 plus H2. Method of observation. The ethynyl radical is observed in the microwave portion of the spectrum via pure rotational transitions. In its ground electronic and vibrational state, the nuclei are collinear, and the molecule has a permanent dipole moment estimated to be E equals 0.8, debye equals 2.7 times 10⁻30 coulomb. The ground vibrational and electronic state exhibits a simple rigid rotor-type rotational spectrum. However, each rotational state exhibits fine and hyperfine structure, due to the spin-orbit and electron-nucleus interactions, respectively. The ground rotational state is split into two hyperfine states, and the higher rotational states are each split into four hyperfine states. Selection rules prohibit all but 6 transitions between the ground and the first excited rotational state. 4 of the 6 components were observed by Tucker et al. In 1974, the initial astronomical detection of ethynyl, and 4 years later, all 6 components were observed, which provided the final piece of evidence confirming the initial identification of the previously unassigned lines. Transitions between two adjacent higher-lying rotational states have 11 hyperfine components. The molecular constants of the ground vibronic state are tabulated below. Isotopologues. 3 isotopologues of the 1,2C12CH molecule have been observed in the interstellar medium. The change in molecular mass is associated with a shift in the energy levels and therefore the transition frequencies associated with the molecule. The molecular constants of the ground vibronic state, and the approximate transmission frequency for the lowest 5 rotational transitions are given for each of the isotopologues in the table below.